today's topic is about condensation. So previously we already learned about the boiling, and then in this video I will explain about the condensation. So condensation occurs when the temperatures of vapor is reduced below its saturation temperature. For example, we have water, water vapor. So at 1 atm, we know that the saturation temperature for the water is 100 degrees Celsius. So which means when we want to condense the water vapor, we have to reduce the temperature of the water below water at 1 atm. So that at that pressure, the saturation temperature for the water is 100 degrees Celsius. Therefore, if you want to condense the water, or in other words, you want to turn the water vapor to the liquid, you have to reduce the temperature below 100 degrees Celsius. So water saturation temperature at 1 atm is 100 degrees Celsius, and in order for you to reduce, or not reduce, in order for you to change the phase from the vapor to the liquid, you have to reduce the temperature below the saturation temperature, which is below than 100 degrees Celsius. That is what that is the definition for the condensation, or the when the condensation will occurs. Only condensation on solid surface is considered in this chapter. Two forms of condensation. One is a film condensation, and then the second one is dropwise condensation. Let's take a look at the definition of both of these types of condensation. So first is film condensation. The condensate wets the surface and forms a liquid film. So as we can see this picture here, we have a solid surface, and then what we have here, the condensate wets the surface and forms a liquid film. And then the surface is blanketed by the liquid film, which serves as a resistant to the heat transfer. So as this liquid film form on the solid surface, it will create another resistant to the heat transfer. So let's say you have a cup of water, cold water, maybe at 70 degrees Celsius, and then it will the water vapor out here will be condensed on the surface of this water cup, and then it will form a layer of fluid here. So this layer, originally, if we know that when we do the heat transfer, so we know that this will have condensation here, convection process, and then for the solid surface will have the conduction process, and then the last one here is a convection process. But now since we have a liquid film here, due to the condensation process, what will happen here, we have another resistance here. So it will have another types of resistance, and it will originally we have three resistance in our thermal resistance network. If we have this condensation, we create another form, it will create another resistance. Therefore we have four resistance in our thermal resistance network. So for dropwise condensation, the condensed vapor forms droplets on the surface. The droplets slide down when they reach a certain size. No liquid film to resist heat transfer. So as a result, heat transfer rates that are more than 10 times larger than with film condensation can be achieved. So now we are only in this chapter focusing more on the film condensation. So the film condensation, mostly when we buy laminate, ice laminate, and then we in a cup of in a water cup. So what we can see is, after sometimes we put it on the table, after sometimes it will create a form of layers, liquid layers at the outside of the on the wall of the outside wall of the cup. So that is condensation. So now in this chapter we are more focusing on film condensation. Okay, so film condensation on the vertical plate. So as we can see here, so it will the delta is the thickness. So the thickness is from here to here. So as we can see here, as the x increases, the x starts from the top of the cup, for example, or in this figure we can see that at the top of this solid surface, and then it will start with a 0x, and then it will increase as the as it goes down, the x will increases. So as we can see here, the liquid film here will increase as the x increases. So that is what this statement states, tells us. Okay, the delta increases in the flow directions x. So as x increases, the delta will increase. So heat, the amount of HFG released in the is released during the condensation and is transferred through the film to the plate surface. Okay, Ts must be below the saturation temperature for condensation. So Ts is the surface of this of this plate. Okay, so now if we have a cup of water here, oops, sorry. So if we have a cup of water here, so this, for example, let's say this is the cup wall, and then the temperature here, the Ts here, will needs to be below than the saturation temperature for the vapor. Okay, so at here is the T vapor, and then it will reduce up to the T surface. Okay, this T surface will be below than T saturation, and in order for the condensation to occur. Okay, the temperature of the condensate is T saturation at the interface and decrease gradually to Ts at the wall. So here is a T vapor, and then it will reduce the temperature as it goes to the T surface. Okay, so it starts from the TV and then the Ts, and then it will reduce up to the TV, and then it will reduce to T saturation, and then it will reduce to T surface. Okay, the vertical plate flow regimes, the Reynolds number is the hydraulic diameter dH, rho liquid V liquid over mu1. So you don't have to worry about Reynolds number, because in every of this regime, so we have lamina wave free, and then we have lamina wavy here. So we have lamina wave free, lamina wavy, and turbulent flow. So now you don't need to remember this equation. So each of these region will have its own Reynolds number equation. Therefore, in this chapter, it is your job to determine whether that lamina is in the lamina wave free region, or lamina wavy, or the turbulent flow. So what you have to do is you have to remember all these region. Okay, the Reynolds number below than 30 is lamina, so wave free. And then the Reynolds number in between 30 to 1800 is wavy lamina. And last one is Reynolds number which is greater than 1800 is turbulent. This is for condensation, so you have to remember, okay, the region. So this is the equation that will be used for you to determine the H star Fg. So this H star Fg will be used in each of these equation. Okay, it is important for you to understand which HFG equation that will be used for your problems. So now the first HFG here, modified latent heat of vaporization here, this is for the subcool liquid. Okay, sorry, this is for the liquid that below saturation temperature. So you want to condense the liquid, and that liquid is below saturation temperature. So this is below saturation temperature. For example, you have 100 degrees Celsius, and then your liquid is below than 100 degrees Celsius. It is already below than 100 degrees Celsius. So it is a saturated liquid, and then you will use this equation H star Fg equal to HFG plus 0.68 CPL. This is specific heat capacity liquid, T saturation minus Ts. Okay, so all this information will be you will have to refer to the table, or it already give in the question already given you all this information. So for a vapor that enters the condenser as superheated vapor, so now this is saturated and then this is superheated. So if the superheated SPH, it will reduce to the T saturation first. Okay, this is at T superheated, and it will reduce to T saturation, and then goes to your temperature lah. Okay, T required, for example. Okay, so it will have two steps to go to T required. And what will happen here, we have another HFG for the superheated vapor. This is saturated vapor, and this is superheated vapor. To reduce the superheated vapor to T required, you have to reduce to T saturation first, and then from the T saturation it will reduce to the T required. T required is normally is T surface lah. Okay, T surface of the solid. Okay, so now we will modify the latent heat of vaporization, this latent heat vaporization HFG, to this one. So remember, this is the case where the superheated vapor, so HFG plus 0.68 CPL T saturation minus Ts is the HFG for here. So this HFG, and then now we have superheated vapor case. So we will add these terms, CPV TV minus T saturation here, because we have to reduce the T superheated to T saturation first, and then T saturation reduced to T required. So in this case, for the saturated liquid, what will happen is it is from somewhere in T saturation, it will reduce to the T required. So T required is a Ts lah. So you no need to reduce the temperature up to the T saturation, because it is already below than saturation temperature. Then we have to directly reduce the temperature to T required. That's why the HFG here doesn't have these kinds of CPV. So since this will be added because of the superheated vapor, since we need to reduce the T superheated to T saturation first, and then from the T saturation we will reduce to the T required. Okay, that is the two equation. This equation is important because each of the regime, lamina wave free, lamina wavy flow, and then a turbulent flow will use this H star Fg, and it is your job to determine whether that liquid is saturated liquid. No, that's your problem is in saturated liquid or superheated vapor. Okay, so it is important for you to determine, and you have to know which equation to use to get what is H star Fg. So rate of heat transfer in this condensation will be used these kinds of equations. Since the condensation is a convection process, so we can see here the equation is the same as the convection process. where we have to find what is H, as T saturation minus Ts, okay, and equivalent to M star HFG. So this HFG is based on these two conditions. So you have to determine your problems, either it is in saturated liquid or in superheated vapor. Since we are using the equation from the same equation as convection process, it is important for us to determine what is H. So I will explain a little bit more on how to find the H after this, since this is our main concern in this chapter. Okay, the Reynolds number, so you don't have to worry because each of the region will have a different Reynolds number equation. So the properties of the liquid should be evaluated at film temperature. So if you want to refer to the table, so all the properties must be in the T film temperature. So you have to evaluate at the film. Okay, for the HFG should be evaluated at T saturation, only HFG. Okay, so remember HFG here. So we have here HFG here. Okay, these two equation, you will have to refer to T saturation. Okay, now this is the assumption for film condensation on the vertical wall. So it's okay. I will change to this equation. So this equation, it is in lamina wave free. So this is lamina wave free. So the first regime of the flow, okay, it falls at 0 to 30. So this is lamina wave free. So the equation that will be used in this region is this one. Okay, lamina wave free. Okay, so if you are required to find the lamina wave free H, okay, we want to find H. As I mentioned before, our main objective here is to find what is H. So now we want to find H. We have to determine whether that region is in lamina wave free or lamina wavy flow or the turbulent. Therefore, in lamina wave free, the equation for us to find what is the Reynolds number will be this one. So the K here is thermal conductivity of the liquid. Okay, G is a gravitational acceleration. V here is kinematic viscosity, and then H vertical is from this equation, and then you will substitute into this equation, okay, in order for you to find what is the Reynolds number. So normally we are not focusing more on the lamina wave free because this is the last option for us. So I will talk a little bit more. Before that, I will explain all the equation that will be used for you in order for you to determine what is the H vertical. So for now, for the lamina wave free, we will use this equation. Okay. So the properties of this, will be evaluated at film temperature. Okay, the HFG and rho V are to be evaluated at the saturation temperature, T saturation. Okay, now we go to the wavy lamina flow. The equation that will be used for the wavy lamina will be here, this one. H vertical wavy equal to Reynolds number KL over 1.08 Reynolds number power of 1.22 minus 5.2 G over VL square 1 over 3. So in order for you to determine what is the Reynolds number, you have to substitute into this equation. Okay, so these two equation, is important. First is, sorry, because I had pressed the button on the okay, these two equation is important, 1 and 2 for lamina flow wavy lamina wavy flow. So lamina wavy flow is in regions of 30 to 1800 for the Reynolds number. So this one, Reynolds number is in between 30 and 1800 for wavy lamina flow. So that's two equation is important. And then the last one is turbulent flow. Okay, the turbulent flow, you will use this equation to find what is the H vertical, and you will use the Reynolds number turbulent to find what is the Reynolds number, and then substitute into H vertical turbulent. So the physical properties of the condensate are again to be evaluated at film temperature. Okay, HFG or vapor will be evaluated at T saturation. So now the first step you have to do when you want to evaluate or you want to solve the problems in the condensation, first you have to assume. What you have to assume, let's say you have the equation, the problems, and then you assume that problem is in wavy lamina. The first assumption is wavy lamina flow. So you have to assume wavy lamina, and then after you made that assumption, you go to Reynolds number wavy, substitute all the values, okay, in Reynolds number wavy. So 4.1, 3.7, LK, all this information, plug in into this and find what is Reynolds number. After you find the Reynolds number, compare your Reynolds number with this. Is it in the range of 30 to 1800? If it is in between, therefore you can directly use H vertical. So first, like this. The steps to calculate or to solve the problems in condensation. First, you made an assumption. Assume wavy lamina. So this is your first step. After you assume wavy lamina, you have to go to this Reynolds number equation for lamina flow, wavy lamina flow. So if you assume wave free, then you go to Reynolds number wave free. So first you assume wavy lamina, go to Reynolds number wavy, and then plug in all the values. Plug in, substitute, fill in, and then get the value of Reynolds number of your assumption. And then after you get your Reynolds number wavy, compare to this Reynolds number. Is it your Reynolds number in between 30 to 1800? If it's yes, then you go to H Reynolds number, H vertical wavy. Substitute all the information into this. If not, you have to make an assumption. So this is if yes, and if no. So this is first and second, third, and then this is fourth, and then third is yes. Yes, go to is it in between 30 to 1800? If yes, then go to number 4. So not like this. Okay. Okay, first assume wavy lamina. So that is your first step, and then second, go to the Reynolds number. Then after that, you will compare with this. Is it in between 30 to 1800? If yes, yes, 1, 2, and then this is 3 step, and fourth, if yes, go to the H vertical wavy, substitute the value, and then you will get what is the H vertical. If no, no, this is 4. If no, if you compare your Reynolds number, it is not in between 30 to 1800. If no, so assume turbulent flow. And then you will go to the same step. Assume turbulent flow, and then if you assume the turbulent flow, you have to substitute into the Reynolds number vertical turbulent, all the information, and then compare with Reynolds number turbulent, which is greater than 1,800, and then if it's yes, and then you go to H vertical turbulent to find what the H vertical turbulent. So this H is heat transfer coefficient. So this H will be used in this equation to determine what is the Q condensation, Q dot condensation. Okay, that is the step on how to how to solve the problems in condensation. So if you assume that it is not in turbulent flow, then you have to assume the last one, which is wave-free lamina. Okay, because all those all these two region is not for your problems. Okay, it is falls under the wave-free. So first the assumption, first you have to assume wavy. If not, then assume turbulent. If not, then assume wave-free. So if it is not in turbulent flow, then it is confirmed in wave-free flow. Okay. So some cases we have inclined plates. So what you have to do is to use this equation in order for you to determine what is the H incline. Okay. So H incline is H vertical cos theta 1/4. So this cos theta is the inclination degree lah. And then H vertical will be referred to this flow. Okay. Then you have to assume that is wavy lamina, and then try to find the Reynolds number compared with the range of wavy lamina. If yes, then you go to H vertical. And if no, you have to assume a new one with turbulent flow. And then after you get the H vertical, substitute into this equation. Okay. And times with cos theta 1/4. The same steps as before. Okay. For the vertical tubes, so we can use this. Sometimes we are not go to these vertical tubes. Okay, no need to. Okay, for the horizontal tubes and sphere, we have this equation. So H horizontal 0.729. So this is the equation. And this is for horizontal tubes. Okay, we have to write horizontal tubes and sphere. So for the horizontal tubes, we will use 0.2729. If we have sphere, then we go to 0.815. So take out this 0.729 and then replace with 0.815. Okay, so for the horizontal tubes and sphere, you do not need to assume wavy lamina, turbulent, or wave-free. Okay, you will directly use this equation. Okay, let's say you have a tube in your problems, then you directly use this equation. Substitute all the properties, and you have to find the properties from your tables if it is not given in your question, and then you will get directly the H horizontal for the horizontal tubes, H sphere for sphere. Okay, now this equation is for horizontal tubes. So if you want to find sphere, H sphere, therefore you have to change 0.29 to 0.815. Okay, so that is for horizontal tubes and sphere. So for the horizontal tube banks, you will use this equation. Okay, so N here is a number of tubes in a row. So for example, you have these types of arrangement. Okay, So these types of arrangement, we will flow the liquid. The liquid will flow from top to the bottom. So what we have here, we have two columns here, and then 1, 2, 3, 4, 4 tubes in a row, 2 tubes in the columns. Okay. So in this equation, n is referred to this number. So you substitute this number into this, okay, to find what is the H horizontal and tubes. So again, you have to find what is the H horizontal, 1 tubes, by referring to this equation. Okay, substitute into this equation for horizontal tubes first, and then go to this equation times with 1 over n to the power of 1 over 4. N here is referring to number of tubes in a row. Okay. So other equation that can be used in order for you to find what is H horizontal is by using this equation. Actually, this equation is the same as this. This is the simplified version of this equation. You may directly use this equation to substitute all the information, all the values inside this equation, and then you will directly find the H horizontal. Or maybe you want to do one by one steps, and then you have to find what is H horizontal tubes by using this equation, and then find the number of tubes in a row, and then substitute into this and times with both of these value, then you will get H horizontal and tubes. Okay, so that is horizontal tube bank.